All right. So we've been talking about how systems can change their behavior. And we've been mostly focusing on attractors, attracting invariant sets. Last Thursday, we were looking at how equilibria or fixed points can change. Well, or for that matter, even just be created out of whole cloth as we vary a parameter. That's the notion of a bifurcation. And there were two kinds, roughly speaking, of change. The first few examples were local in the state space, where the fixed points, as they changed their stability or were born, sort of happened in a small region of state space. And then we looked at what were called catastrophes, where the change, and you might think of it as the whole attractor basin portrait architecture, would shift such that a stable equilibrium might disappear and you have to flow sort of arbitrarily far away to some other stable fixed point. So, and the surprise there, most of that was developed in the 50s and 60s, was even though you're slowly changing your control parameter, you can get this massive change in equilibrium. And I kind of gave a little side discussion about climate change. Is it going to be a local bifurcation, or is it going to be a catastrophe? And now we understand that word in two different senses, mathematical and maybe societal, environmental. Okay, so, and there's a fair amount you can do. You know, I sort of ended up with yet another classification scheme. We didn't go into detail in the classification scheme for these different kinds of catastrophes. But it's a fascinating subject and gets applied a lot, certainly in engineering systems these days. And worth reading at some point, flesh out one's intellectual repertoire. But we're going to move on to talk today now about bifurcations between time-dependent behaviors. So what kinds of behaviors do we have? Well, last Thursday it was just fixed point to fixed point. Fixed points losing stability, gaining stability, appearing out of nowhere. Here we have fixed points, say, going to limit cycles, chaotic attractors, limit cycles going torus or quasi-periodic behaviors, and so on. So I want to show that today. And it turns out, and this shouldn't be any kind of surprise, that trying to describe these bifurcations between time-dependent behaviors is a lot more difficult. So what I'm going to do today is mostly give you some simulation demonstrations of what can happen. So this is just to give some visual sense of what's possible. The take-home message is pretty simple. Anything is possible. So I'll just show you, a couple favorite quote bifurcations. Now, before, I gave this definition of a bifurcation, which is not the technical way that Strogatz uses bifurcation. In the history of the development of bifurcation theory, bifurcation meant that an eigenvalue was going through the unit circle, roughly speaking. And here, in today's examples are going to kind of emphasize this point. This is a looser notion of bifurcation, because the more technical one about the change of eigenvalues going between, below 1, above 1, or if you're in a discontinuous system, positive, negative. There are qualitative changes that we're interested in that don't correspond to that change in the eigenvalue spectrum. We need to introduce a generalization of that kind of time-averaged eigenvalues to describe a little more quantitatively what's going on with bifurcations between time-dependent behavior. So today's lecture, I'm going to end up with a much simpler example than the first bifurcation examples with differential equations. We'll go back down to one of these return maps, a one-dimensional map, and study it there, where we can be very precise about bifurcations in Strogatz sense and bifurcations in this more general sense. So bifurcation, qualitative change in behavior when a parameter slowly varies. And the idea about slowly varying the parameters is that you, with your hands on the knobs that are attached to this gray box, are not adding your own dynamic to the system. And if you took the knob and moved it back and forth, then the thing's going to oscillate because you're driving it. So here what we mean is that you sort of arbitrarily slowly change the behavior. The system is always in its attractor, appropriate for that parameter setting. Okay, so and the first system we'll use, we've already looked at when we talked about two-dimensional flows. This would be the van der Pol oscillator, except now what we're going to do is drive it periodically. And this is actually what van der Pol did back in the 20s. That was a sine wave generator, and he was driving his electrical circuits that were roughly modeled by this nonlinear differential equation. And he could vary the frequency and the amplitude. And then we also have a couple other control parameters. Mu is just sort of the size of this whole coefficient in front of x dot. If you remember last time I mentioned that, crudely speaking, when you look at a second time derivative equation like this, you can think of the coefficient in front of the x dot, the first derivative term, as proportional to a dissipation of friction. And here, what van der Pol is doing is he's varying this coefficient of friction or dissipation depending upon where the state is. Close to the origin, this is negative. If x is large, it's positive. So it's kind of self-regulating how much dissipation it has. So either taking energy away from the system or adding energy to the system actively. Okay, so in the case we talked about before, we weren't driving it. And we saw that this had a stable limit cycle. It was one of the first. Although it turns out, I was just reading over the weekend a biography of Poincaré that just came out. And apparently Poincaré talked about circuits like this 20 years before van der Pol. So, a series of lectures he gave to electrical engineers in 1908, apparently. I haven't read the French papers yet. But, and he actually talks about self-stabilizing limit cycles. So, it's an older idea. Important one, again, right? It's important to have a system that has a stable oscillation so that you can tune it to stable carrier frequencies and radio circuits and other things like that, or have a heart that beats regularly. Very useful to have that. Whereas the simple harmonic oscillator is not stable in the same sense we mean attractive invariant set. Okay, so now I want to talk a little bit about this, the driven version of the van der Pol. Or maybe I should also mention the van der Pol, this kind of state-dependent dissipation also shows up in the propagation of spike trains and neural axons, called the Fitzhugh-Goodman equation. Similar dynamic. Not exactly the same form, but that's a partial differential equation that sustains traveling waves called spike trains. So it's a useful mechanism to understand. And now here we have this driven version of this. So when it was undriven, we had two-dimensional state space, position and velocity. Right? We had specified two numbers that determine the current state and flow in the plane. And now the question is, what dimension system is it if I drive it? In this case, periodically. So I'm going to argue that we should think about this as a three-dimensional flow. And then most of the examples I'm going to show you graphically in the simulations, you're going to have to imagine an object in 3 dimensions, just like the Bristler and Lorenz attractors. So why is this a three-dimensional flow? Well, we still have position at each moment and velocity at each moment. And now I want to think about this driving term as I'm going to invent a third variable, call it phi for phase, and write out the equation in terms of this phi of t. Right? So this is going to be just the phase is constantly increasing, but is mod 2 pi because it's a phase. It just goes around. Right? So we're going to think about a third sort of concocted variable here and replace this explicit time-dependent driving term with phi, and then rewrite the equations as 3 first-order equations, and that'll sort of constitute the argument that it's a three-dimensional dynamical system. So the net result is that the state space is periodic in this third variable, and we're going to think about the structure of the state space as a plane with cross product with a circle. Okay, so how do we do this? I'm also illustrating here how we change a high-order time derivative into a set of first-order differential equations. So this is second-order time derivative here. So I invent a new variable, call it y, and that will be x dot. And then, of course, y dot is then x double dot. So then on the right-hand side, I have these terms here, including the driving term. And now here's my third invented variable phi, and that just increases linearly with time. Except now I think of the state space as the plane across the circle. Plane across the circle. The other way to say this is that when I write out these three first-order equations, the vector field has a symmetry. Namely, this third variable phi just repeats every 2 pi. Therefore, I can kind of mod out. I mean, you can think of this as a proxy for time. And then you'd say, well, the state space is 2 dimensions across time, r. But since the vector field where the vectors are pointing, that exactly repeats every 2 pi for phi. So I can kind of mod that out and get a compact picture of what the state space is. Okay, so this is one way to figure out what the dimension of your system is. You try to rewrite everything as a minimal set of first-order differential equations, inventing variables y here or phi here as needed. Okay, so everything is going to be kind of like in kind of a solid donut, I guess, solid torus. Okay, now let's see if I can get the demos to work here. This will take a little bit of sleight of hand, so you have to be a bit patient. Most of the things I'm going to show you, you can redo in Sage with differential equation integrators we give you. Okay, so the first thing is just to show you that we can go from what we already know about the van der Pol. It has this dog-bone-shaped limit cycle. Again, tracting from the outside, tracting from the inside like that. And then as we vary, in this case, the frequency in this range, you go from a system essentially having a dominant frequency, the time it takes to go around the loop, and maybe some harmonics because it's not exactly a circle. There'll be some higher frequency components that make that dog bone squarish kind of shape. It'll shift over to, again, now you have to think about this donut picture. There's a second frequency, which happens to be, depending upon exactly how you drive it, incommensurate with the base frequency, and then it's sort of like a Lagrange figure, if you remember your first year playing around with your oscilloscopes in lab, physics lab. It kind of rolls around, and there's the system responds with a different frequency that is the product of the result of the driving frequency and then the natural frequency of the limit cycle. Now, no longer is there really a natural frequency of the driving cycle. It's being driven and it's responding nonlinearly, but there is a frequency response when it's just a simple limit cycle. You can approximate very well. But then the result is you should imagine now this is the surface of a donut, with the solution kind of winding around the donut and never attaching to itself again. Otherwise, it'd be periodic. So it just fills out this whole surface here. Okay, let's see if I can. Yeah. No, that's actually, it's a little bit driven. So the question was, is this one over here the undriven? No, actually, the undriven van der Pol has kind of a square and more rectangular shaped limit cycle. So this is already being driven. And all you're going to do is I'm actually varying the frequency, not that much, from 2.1 to 2.15. So this change is happening over a very small range of parameter. So this first limit cycle that we're in. Say again?
Is 2.1 closer to the resonant frequency of the system?
That's a good question. So is somehow the starting value of the control parameter, where the frequency is 2.1, is that somehow closer to some kind of natural response of the system? So this kind of resonance. Yes. However, we have to loosen up our notion of what a resonance is. What you're going to see in all of this is even, okay, so what's the typical notion of resonance? So the classic one, of course, is they show you the Como Narrows Bridge, right, with the wind up and, the thing, finally, all the wind blowing, it starts oscillating and just collapses. It's something about the natural frequency of the bridge and the energy from the wind adding in response at one frequency that happens to be very destructive, and it's unstable. So the energy keeps piling into one mode. What you're going to see in these nonlinear systems is that they have many, 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 many resonances. Even if you vary the parameters just a little bit, you'll be stepping across an exact one-to-one resonance, one cycle of the driving oscillator, one cycle of the response, but it can be 2-to-1 or 3-to-1 or 4-to-5. You'll see when we go through. So hopefully the simulations will come across on the camera, but as I'm sort of animating the variation of the parameter, you're going to see different things lock in and unlock. And what that corresponds to, and we'll probably see it in this sequence here, is suddenly this won't look like a solid surface of a torus, but you'll see 2 cycles this way and 3 this way. They'll be different. Well, we do call them resonances, but these systems aren't. To say that there's sort of one resonant frequency of a system greatly undervalues the richness of what can happen. So let me go through some examples, if that gives you some idea here what to expect. A limit cycle to a torus. And then the next example will be going from a limit cycle to chaotic behavior. Probably also notion that the idea that there's a clean bifurcation as you vary some parameter starts to get a little more muddied with these examples. But we'll come back and sort of work that through when we have some quantitative measures of stability. Okay, now this is a slightly different driven van der Pol. I call it Shaw's deviance. So Rob Shaw's a colleague of mine. And way back at UC Santa Cruz in the 70s, when we were playing with these things, we didn't have these nice digital computers. We had analog computers. Basically, a pile of modules that added and multiplied voltage together. So continuous state computers. And this particular version of the van der Pol, where the driving term, see now I've just written it as its 3 first-order equations. So what happened is Rob misprogrammed the analog computer. How do you program an analog computer? Well, you take the output of the integrator and run it into the multiplier, and then that signal goes into the adder with the other one. You basically build up a circuit diagram. Misprogramming doesn't mean you typed the wrong character on a keyboard. It means you plugged in the wrong units together. Well, in this case, it was very easy. We had a sine wave generator, and we just plugged it into the x dot, what was the x dot equation, the x dot integrator. Very easy to play around with different systems this way. Also, the other nice thing about analog computers, they have knobs. The program I'm using now is awkward to use. It's very old. It's my own design. I'm not blaming anyone. But I like knobs, partly from this analog computer. Anyway, so why would you ever put a driving term up here? No reason. Van der Pol never would have thought of this, because he was thinking back in terms of that second-order equation with the kind of right-hand side driving it, thinking about in those terms here. You could plug in the sine wave generator wherever you want, whatever, x dot, y dot, z dot. Right? So, okay, so I have to change the equation here. Oh, well, okay, the benefit of this, the punchline actually is when you drive it sinusoidally, you drive the x dot equation sinusoidally, it's much more interesting. It's much less stable and more chaotic. So that's why it lived on in the, all right. And then another, well, I think this pushes the boundaries of the meaning of bifurcation, but just to show you what happens when you're up in a chaotic regime and then you vary parameters. So it's going to be pretty much the same parameter, mu, that we're varying. We're going to use this coefficient in front of x dot, but now a larger value, 9 to 10. And stuff just happens. It's hard to use a phase plane analysis at this point to see what's going on. It just looks complicated. Here's just kind of a final one for the van der Pol. We'll go from, this one's kind of nice. Illustrates a couple nice its topological features. We'll start with a chaotic attractor. Again, still Shaw's van der Pol. And then we're changing now the amplitude, driving amplitude here in a small range. We're going to end up on a torus attractor, quasi-periodic behavior. Right. So, lots of things can happen. And again, you know, it's not like the form of the equations was changing a whole lot. All we're doing is varying driving frequency, amplitude, that kind of dissipation coefficient in front of x dot, and you're getting these wild variations in response. So there's a challenge there to try to describe what's going on. So
question.
Yeah.
If you limit yourself to parameters only of a certain like small integer ratios, rational numbers,
right?
Is there any sort of type of parameter? Because these changes seem to be, you know, you're highlighting how they're just qualitative and different kind of systems, even though the parameter is smoothly changing.
Right.
But maybe there's like a subset of parameters in the continuum that represent particular shapes. Is there anything like that, maybe?
No. I mean, probably the simplest response to that is you can't really, maybe as a corollary of this. So the first thing is, and I was kind of emphasizing this when we looked at the Rössler equations, right? The Rössler equations, there's only one nonlinearity. It's this ZX multiplication. Take that away, completely analyzable. Same thing with some kind of a numerological interpretation of the form of coefficients. Typically, you can't look at the parameter value and predict what the behavior is going to be. Now, I will contradict what I just said. There'll be lots of particular cases I can go through, but in general, there's no sort of recipe. There are certain bifurcations and bifurcation sequences where you can see that. There's certain kinds of very, very simple maps that were developed to describe quasi-periodic behavior. These are called maps of the circle, and there's kind of a relationship between the coefficient, which is the amount of offset per iteration, and whether that's rational or irrational. But it's a really simple setting. So for sort of classes of system, there are rules, but no general methodology to look at the equations or the coefficients, the control parameters. Unless you set them all to 0 or something. So, okay, so now, maybe as an antidote to that kind of visual complication that we just saw, I want to study a system that's kind of non-trivial, the Rössler system, and kind of delve down in some more detail. So this will be an example where we do know quite a lot about the behavior and how the bifurcations occur. The driven van der Pols, or I just put that out there because I don't think anyone's actually really analyzed the chaotic attractors of the van der Pol in any kind of detail, like we're going to do now for the Rössler. So this is a little, again, show that there is some order in the chaos here. We're going to study the Rössler again. So three-dimensional system, basically a linear oscillator in x and y, and then there's this kind of stable, unstable behavior when x passes the value c. Roughly speaking, well, we usually set A to 0.2, B to 0.2, and then C is about 5.7 for this chaotic attractor that I showed you before. So what we'll do here is actually lower the C value and show you where this chaotic attractor comes from as a function of parameter value. So there's actually a quite ordered sequence of bifurcations that leads to this object, and it actually helps you understand how the chaos is structured. It's called the period doubling sequence. And we'll study this through just some simulation demonstrations. And then we'll reduce dimension and study a one-dimensional return map version of this to understand the period doubling sequence in more detail. Okay, so the first thing is, first bifurcation sequence I'll show you is just going from a fixed point. In fact, you can barely see that For those of you in Berkeley, my finger is at a dot. And then that goes unstable, and we end up with a limit cycle. This is one of the first bifurcations, Hop, so-called bifurcation, that was studied in some analytical detail. For something more interesting, we're going to now increase the C value from 1 to 4 and go through the limit cycle, period 1 limit cycle, to first bifurcation. Well, the limit cycle gets larger, and then it takes 2 times to go around. So we call that a period 2. Right? It's twice the period of the original one. And then, amazingly enough, this happens again. This period 2 limit cycle splits, kind of a smaller amplitude splitting, but then it has to go around 4 times. You follow with your eyes around before it comes back to itself. So again, if we wanted to think in kind of Fourier or frequency terms, we'd have one dominant frequency here. Well, here the whole set is getting larger, so the amplitude would grow. It would be louder, more energy in that peak. And then when this bifurcation occurs, there's now a component of the behavior which happens at twice the time period, or half the frequency. So you'd see a dominant component in the Fourier spectrum, and then as you go through this bifurcation, you'd see this peak coming up at half the frequency. Then up here, what happens, this happens again. So now you have the dominant frequency, the subharmonic, through the period 2, and then between those peaks, you have another subharmonic that's at 1/4 the main frequency. So there's a very particular frequency signature as you're going through this sequence. In fact, that was used in the very early days of trying to analyze fluid turbulence to see if there were these strange attractors. This is bifurcation sequence. It was actually seen in turbulent fluids. It's kind of a hint that something was going on. A flow that somehow, for some reason in the turbulent flow, sort of looked like the Rössler system. Right, so the next thing is sort of on the other side of this. After all the period doubling has happened, you end up with, in the kind of terminology, you end up with bands. So the way to think about this is, it's this object here, this is sort of like a period 4 orbit, except that within the, so we see 1, 2, 3, 4 bands. Within the bands, the thing is hopping around chaotically. And then as we increase C more and more, what happens is that these bands thicken up and they merge pairwise. So, perfect example of the sloppy use of the word bifurcation, just because these bands merge pairwise. So here I have 2 thick bands. There's still this overall periodicity. It takes twice as long to go around before it connects back up again. So think of this like a ribbon. Some sort of strange, non-orientable Mobius-like ribbon. Until finally, at the parameter setting that Rössler first published in this, we have what we've been looking at, this kind of single band chaotic attractor, whose rubber sheet geometry we described. So, yeah.
How much of this is just the property of resolution, right? If you shrink the gaps down, you get a limit cycle. How much of it is? It's just like numerical. Just we can't accurately resolve. Right? If you shrink your band and say closer and closer, thinner, you can't resolve it.
That's certainly true. I mean, that's I know where you're going, but right. Think of it in lower C values down here. I would have 8 bands, 16 bands, and then over here I'd have 16, period 16, period 32, and they all kind of come together. So at least in terms of resolution of parameter, this thing, how would you shrink it? If you rescale the whole thing, it turns out in this gap here is a period 1 orbit limit cycle that's unstable, and that doesn't change when you rescale the state space. Now, there's another way to think about resolution. I could, for example, look at the differential equation and say, well, that's not physically realistic. These things, if it's from a turbulent fluid or electronic circuit, there's always noise. So people have studied what happens when you add noise to these chaotic systems. It's like, well, in fact, the early days, it was quite controversial. It's like, oh, that's nothing but error. And it's kind of true in a way. But what we're interested in is the overall geometry, and that's sort of invariant. So you can study this period doubling bifurcation sequence, both the chaotic and periodic side, by adding noise and seeing how noise level washes things out. So I'll come back and describe it.
Yeah, period doubling, it looked like it came out fairly continuously.
On the period doubling side, right.
On the period doubling side, it's like it emerged
right.
fairly continuously.
Right.
And so it's just the question is that property of resolution, or is it like how?
Right. Well, it's so much a function of your resolution that there's a systematic renormalization group description of exactly how much resolution you need to see the next level of bifurcation. So what we're going to do, well, I'll show you to kind of finish up the period doubling sequence in the Rustler, and then we're going to shift back to the one-dimensional map, and you'll see in detail how this goes, and there's a lot that's understood about that. So it's a nice example of these techniques from phase transition theory called renormalization group. This is all extremely systematic, so we do understand a lot of this. Okay, so let's check that out just to emphasize that. Right, so here, so we just did a large range of that C parameter from 4 to 6. I'm just going to zoom in, 4.7 to 5.2, much smaller range. And starts at period 5 and ends at period 3, but there's a lot of mayhem in between. So the parameter values were done experimentally. So we kind of came to call what we were doing experimental mathematics, which wasn't a phrase that was accepted early on, but most of the interesting, complicated phenomena were discovered by doing some simulation work. That's not entirely true, of course. I mean, even if you go back to Poincaré, remember the story about the three-body problem, he basically understood the mechanism that leads to this chaotic behavior back in 1890 without doing any simulation work at all. So it took hundreds of pages of mathematical analysis, but there are other topological forms of argument that lead you to kind of an indirect conclusion that the behavior can be very complicated. So, but you know, the Robshaw's variant of the van der Pol, that's purely an accidental discovery. Very helpful because of certain things we wanted to understand about quasi-periodic behavior and the appearance of chaos in that. The work done with the Rustler system, Otto Rustler had mostly studied just that single band attractor. And so my research group, we did a lot of the work on the period doubling analysis of that, but that was all kind of experimental. There are other interesting wild things that happen when you put C equal to 10 and 12. Yeah, so a lot of experimental work. And in the, sort of the early days for this, the modern era of dynamical systems was sort of the 70s. Machines were very slow back then, so this kind of thing I was doing would take us a full afternoon. All the demos I just gave you was kind of messing around. There was a very large benefit, as I said before, to having an analog computer. Partly it was analog signal, so you could plug it into your stereo and listen to it. The ear is a pretty good frequency analyzer. So, and then having oscilloscope traces and that sort of thing. But that didn't stop us from going down to the art store and buying 10 pounds of clay to try to lay out what the shape of this rubber sheet manifold is for the Rustler and Lorentz. It was just, it wasn't clear, so you had to just look at it from different projections and do different parameter ranges. And, yeah.
So when you were listening to it, when you went into those periods of chaos, would it just break into like a white noise, and then all of a sudden you'd hear a frequency emerge, and then it would go back to white noise? Is that the sort of sounds that would generate?
Excellent question. Let's see. Why don't we?
I don't have my sound files.
No, I've got it. Yeah, I had to recompile it too. So let's see. I was going to do that at the end, but maybe why not now? Okay. Right. Okay. So so just sort of by way of summary, there is quite a bit of structure as we vary the control parameter in how the bifurcations occur. And this was actually appreciated even early on, in the early 60s, a Swedish mathematician worked this out. So generally, the period doubling route, we go from period 1 to period 2, period 4, period 8, accumulates very, very quickly, going period 2 to the end, and then in some sense, we have infinite period. Once that is reached, then we have infinite number of bands, whatever that means. Basically, 16 bands goes to 8 bands, goes to 4 bands, goes to 2 bands, goes to 1 band. Okay, so it's very almost symmetric. On one side, it's period doubling. On the other side, it's band merging. In fact, they're described by the same quantitative scaling properties. This question we had about resolution. How wide are the bands when we vary the parameter to the next band merging? That's very systematic. So this is this ordering here is even richer. So it's called the Sarkovsky ordering. And for all the systems that go through this kind of period doubling, and I'll focus on a one-dimensional system that does this too, not just the Rissler, there's this very strict ordering. In fact, one of the interesting things is that, in fact, there's kind of a famous first paper, or a famous title for the paper, called Period 3 Implies Chaos. And the net result of this ordering is that if there's a period 3 orbit, if you can show your system has a period 3 orbit, then it has periods of all orders. Now, they're unstable, but it's very, very complicated. So, and then this result from the 60s is actually just derived topologically. Okay, so let's drill down a little bit with this period doubling behavior. And what we're going to do, if you remember back to earlier lectures, is we're going to think about the Rissler in terms of a maximum X return map. Oh, sorry. Yeah, it characterizes. Actually, I can do that in terms of the one-dimensional map we're going to go through. It turns out there's a certain, call it permutation or stretching and folding in the state space that in order to support the period 3 orbit, that folding is complicated enough to support all the others. I think it'll be easier to point that out in the one-dimensional map we'll look at. Okay, so what we're going to do, remember the reduction, and we do this all the time. We have this continuous time Rissler system, but what I'm going to do is look at, if this was the x-axis here, look at the maximum values in x and plot them. So it's like discrete events every time around. If I started here, right, the Rissler system goes like this, goes to the maximum peak, comes down here. So that would be the next x max value. That comes around here, and then I have this x max value, and so on. So just collect that time series. And I showed you before, when you do that for the Rissler system, you end up with this, it's a function. Right? Previous x max leads to a unique next x max. If I have a particular x max I'm looking at, though, that's ambiguous. It could have come from 2 previous x maxes. So the way I think about this, in fact, it's a little bit of a visualization exercise. You can see in this little quadratic-like function, this return map, the whole geometry of stretching and folding. So imagine I start with some interval here, all parallel states. Then what the map is saying is that I take it up, I stretch it out, and then I project it down. And then I do that again. So our canonical model of this is the so-called logistic map. And it's just, we put in a control parameter here to control the height. So r times x times 1 minus x, or if you plot it out, so we have a one-dimensional state space, and we have this parabolic function of this over the state space that takes xn to xn plus 1. And what we'll do is we'll study that as a function of r. And so this is the classic example of a period doubling sequence. It's the easiest, or I should say lowest dimensional system one could study this thing. Just a discrete time map. And we're going to go back to some of our fixed point analysis just to look at some of the first bifurcations in detail. It's much easier to do this in the one-dimensional map than for the Rissler continuous time system and analyzing its limit cycles. So this control parameter r gives the height of the map. When r is equal to 0, it's just 0. When r is equal to 4, this parabolic function goes all the way to the top of the interval. So in other words, r over 4 is the height of the function's maximum. Okay, and that maximum, convince yourself, that's at x equal to a half. And the way, well, again, first question, dynamical system, first question, where are the fixed points? Well, there's a graphical way we can do this, since we're looking at low dimension. The nice thing is we have the state space cross itself, and we have to get the plot the right-hand side, the dynamic. And the way we look for fixed points in one-dimensional maps is, in fact, I almost always do this even if I'm drawing it by hand, I always put the identity. or x equal y, or x of n plus 1 is equal to xn. Why do I do that? Well, wherever the function crosses that identity, that's a fixed point. And at least the way I've drawn it here, R is small enough that there's only one intersection with the identity. That's x equal to 0. In fact, that's always going to be a fixed point as a function of R. Okay. And we can check to see if it's stable by looking at the slope there. And the slope is, in fact, less than 1 when R is between 0 and 1. Okay. The other way to look at this, again, would be a type of graphical analysis you could do by hand, is you draw your map out, and if I start at a particular x value, I look up what the next x value should be. That would be, x1 would be here. Sorry, x0, this would be x1. The kind of quick way to sort of iterate the map is rather than taking x1 and putting it down here and doing this again, is you reflect off the identity. It's called making a cobweb diagram. So I start with x0. I take f of x0, that would be x1. Then I go over to here, and then I just reflect off of it, and this is going to be the value for f of x1, reflect off of this, and so on. And in this particular case, what you can see is wherever you start, as you iterate this graphically, it's just going to head down towards the origin. Mathematically, you just go calculate the slope and show that it's less than 1, which is a very local analysis around there. Okay, so what happens there? Well, for some range of R value from 0 to 1, this is the only fixed point. But if we make a bifurcation diagram of that, we can easily go above 1. So here was the sort of trivial fixed point at the origin that I just showed you, and it's actually stable all the way through this range of R from 0 to 1. And then at R equal 1, what happens is that, well, again, there's still the fixed point at the origin, but the slope there is now greater than 1, which means small variations get larger. So it goes unstable, and then we have a branching off of the origin of another fixed point called the non-trivial fixed point. It should look like the kind of half of a pitchfork bifurcation. And what's going on there is that the map has punctured above the identity. So it crosses not only at the origin, but also at another point along the identity. And you can calculate that pretty easily. So now this is when R is between 1 and 3. And you can solve for the fixed point there. It's 1 minus 1 over R. So 1 over R dependence. You can try to calculate where the bifurcation occurs by asking where did that trivial period 1 fixed point lose its stability? Well, that's where the absolute value of the slope is 1. Right? It's stable if the slope is less than 1. It's unstable above. Therefore, the bifurcation value is when the map evaluated at the fixed point, its slope is 1. So you can work that out here. Right? Simple function, rx1 minus x. Take the derivative of that. That's just r minus 2rx. The fixed point at the origin, I evaluate the slope. Well, the slope is just r. Easy enough. So r less than 1, it'll be stable. R greater than 1, it's unstable. So that explains why this stable fixed point goes unstable. But now we're actually interested in that fixed point up there, which, again, you can just solve. Once you factor out, x equals 0 is one of the fixed points. It's easy to solve for f of x equal to x. And you get that 1 minus 1 over r parameter dependence. And then we can keep increasing the parameter value. So we previously just saw there was this non-trivial period 1, 1 minus 1 over r, up to 3. But then it goes unstable. So actually what I'm showing you here are just the stable fixed points. Actually iterating the map to do this. And if it's unstable, transients will get thrown away. And then we have another one of these pitchfork-like bifurcations. So this stable period 1 fixed point, non-trivial one, continues on. It's still here, but it's unstable. So if I show you iterates of that, you're not going to see it. Instead, what you get is a period 2 orbit for each value of r above 3. And we can do the stability analysis. That gets a little bit trickier. So one of the things you can do here is look at the this period 2 orbit up here, not as an alternating sequence, but you can look at the second iterative of the map, f squared, and look for fixed points of it. So there's this little equivalence. If I have a period 2 orbit with 2 values that hop back and forth every other iterate, what I can do is look at x values such that f squared takes that value back to itself. So I can either describe it as a period 2 orbit or as fixed points of f squared. It's like I looked at the map every second time. But then that starts to get fairly complicated, right? F squared is the 4th order in x equation, and trying to find roots of that is something you'd probably ask MATLAB to do for you. So directly finding where the period 2 orbit can be done. Typically, you just use numerical approximation to iterate these equations to zoom in on it. To find out where the bifurcation is, though, you can just ask for where the non-trivial period 1 orbit goes unstable. So the fixed point analysis can be carried out, and you can quite accurately calculate and then approximate the r values where you get the period doubling. Right? So the easier analysis here is to not ask where is the period 2 orbit stable, but where did the previous non-trivial period 1 orbit go unstable? That's easier. Because it's just a fixed point, it's not periodic. Right? So that was parameterized as a function of r is 1 minus 1 over r. And we can calculate the slope there. Right? That's the slope. Substitute in here, and we have the slope here is just 2 minus r along that whole arc from the birth of the non-trivial period 1 to where it goes unstable when period 2 appears. And we have 2 solutions to that. So marginal stability, again, is where the slope at the fixed point goes from less than 1 to greater than 1. So that's our condition for the bifurcation occurring. And so we have calculated the absolute value of 2 minus r being 1, and there are 2 ways to satisfy that. One is where it goes stable down here. Right? That's where the trivial fixed point went unstable. It gets stabilized there. And then it goes unstable at r equal 3. Right? So just looking at the whole parameter range. This guy goes unstable down here. In the previous slide, we analyzed the stability of this. This goes stable here. This is 1 minus 1 over r, and unstable up here. And these are probably the 2 bifurcations from the non-trivial to non-trivial, and period 1 to period 2 that you can sort of do by hand this way. This is just showing that non-trivial period 1 going unstable and the period 2 stabilizing. But then we can keep going. Just keep going. Increasing r 3.4 to 3.5. You see that the period 2, it goes unstable, again not shown, and we have a period 4 orbit. It goes high, low, low part of the high part of the low, and back again. There's a particular visitation sequence of the period 4 orbit, and so on, period 8. So the logistic map, as you vary r, it goes through exactly the same period doubling sequence that the Rissler did. And we can see a little more directly why. And if you wanted to look at, actually analyze where the period 2 orbit turns into period 4, it's just very hard to solve by hand. So you usually do this numerically. And there's a general recipe for doing this. If you want to know if there's a periodic limit cycle, periodic orbit to period p, well, that just means there's a series of x values that comes back to itself after p steps. And what you can do is, again, this trick, rather than trying to find these p points, I can look at f to the p and look for fixed points. And that's an equation, algebraic, maybe messy, right? I mean, if f is quadratic, f to the p is going to be 2p, order 2p, very messy. But at least we have this algebraic criterion, and then we have our condition for stability, that as the system hops along the states in the period P orbit, the net stability is determined by the slope. Or again, using this trick, we can just look at the slope of f to the p at the value we're interested in and see what the slope is. Apply the chain rule. You get a very simple criteria for the stability along the orbit. I just unpack. The derivative of f to the p is, I can look at the derivative of the map itself, f, at each point along the orbit, and I multiply those slopes together. That will actually be d dx of f to the p. And then our criterion for marginal stability is that product, absolute value of that product is 1. So this is a recipe that you can sort of code up if you want to search for periodic orbits. Where's the period 3? Where's the period 5? Where's the period 7? Kind of hunt around, and then you can use this criteria to determine if the system is stable there or not. The other thing that happens here is you notice that, so we have this period P orbit. If any one of the points is a half, right? The half is where the maximum is. Slope goes to 0. That product, that wipes out the whole product, and the slope is 0. That's very far away from this boundary of marginal stability. That's extremely stable. They're called superstable orbits. Right? The map where the slope goes to 0, locally things are infinitely contracting. Like very nearby orbits get mapped right on top of each other. So that's another criteria you can look for, these superstable orbits. Okay, now kind of stepping back, we can go up from where the period 2 orbit first appears and go ahead and go all the way up to the largest value of x that gives us an attractor that's already before, and we get this overall bifurcation diagram. Period 2, period 4, period 8. Here are 4 bands merging to 2 bands, 2 bands here merging to 1 band, and then of course there's all this sort of chaotic behavior. It's all punctuated by these periodic windows. This is period 3, and you can see in here that it has its own little period doubling sequence. It goes period 3 to period 6. A little hard to see up here, it's too compressed, but in fact, overall it's 1, 2, 3, 1, 2, 3, visiting like that, and then there's this period doubling. So in this period 3 window, you have the entire period doubling sequence again. So there are a couple of different levels of structure here. One is just the kind of mere properties of the period doubling and this pairwise band merging on the chaotic side. And you can sort of see the band mergings here kind of come down. This 2 bands merging to 1 in a kind of zoomed in parameter range. There's a way of, there's a criteria for that. You've kind of, maybe you noticed just visually, kind of squint your eyes up here in the chaotic regime. You can see that there are these dark lines. We call them veils. It's where the density of the chaotic orbits is highest. And these are images of where the slope goes to 0 at the maximum, because it's most contracting. So the band mergings occur where these veils, this is the first iterate of half, second iterate of half, third, fourth, and fifth, they all overlap here. In fact, they overlap right where that non-trivial period 1 orbit, it's here, but it's unstable. It crosses there too. So these band mergings are, there's a recipe for finding them, which is they become the iterate of a half. The maximum of the map becomes periodic. And this is just a zoomed in picture of that, where you can see all these veils coming in, and they all cross right here. And so that crossing gives you criteria for calculating R values for the band merging. So I won't go over this in too much detail. I should finish up. But there is a way on the slide. It gives a recipe for calculating R values where the band merging is. So we look at the veils are just the iterates of the maximum of the map. First iterate of the maximum, which of course is the upper bound of the attractor. F squared of a half is the lower bound. And then we just look at when iterates become periodic. So 2 bands go to 1, where the iterate of a half becomes period 1. And that gives you this equation where F cubed of a half and F4 of a half are equal. And then that you can use a solver in the control parameter R to show that the value, parameter value where 2 bands merge to 1 is about 3.67. This is just a zoom in to the period 3 window, period 1, 2, 3, and just so you can see the bifurcation happening again. So this is period 6, period 12, period 24. You have 6 bands merging to 3 bands, and then eventually this window sort of disappears and it goes back to the main sequence. And you detect these by looking for these superstable orbits, which are where the periodic orbit has 1/2, with the slope is 0 as part of it. And these are particularly easy to find. You just look for iterates of 1/2 that are equal to 1/2. So this would be the criteria for period 3 orbit having 1/2 and therefore being superstable. So that's an easy equation to solve. And the period 3 orbit is sort of centered around this one superstable orbit at 3.83. It's right about here. Okay, so I will skip the demo for bifurcations. Yeah, so this lecture and the previous one were just giving us a sense of how behaviors can change as you vary parameters, right? I mean, I kind of opened up this whole big picture idea that there are arcs in parameter space that are traced out by varying a control parameter, and we were interested in some geometric topological picture of how those arcs could be punctuated by these qualitative changes. So the period doubling sequence it's a whole series or a cascade of local bifurcations that have this global structure to them. And we'll come back and analyze some more quantitative properties of that sequence in a later lecture. But next what we're going to do is shift back to really focusing on chaotic behavior. What can we say about it quantitatively? What are the underlying mechanisms? So I'll stop there.